Hi, my name is Arthur. I am introducing two speakers for this session. This session is called Intuition versus Reality, Surprising Truths in Python Performance. Here to talk about that is Arthur Pastel and Adrien Cacciaguerra. Give them a warm welcome, please.
Thanks. Hi, thank you for coming. Really excited to show you this interactive talk to talk about performance. And so, yeah, I think we can just give you a small introduction, and then you'll have to use an app to answer a few questions as a quiz, which will end up with a leaderboard and to test your basically performance intuition and measure it against reality. So a little introduction first.
Yeah, so Arthur and I are software engineers by trade for more than 7 years now. We met in engineering school 10 years ago. And yeah, 2 years ago, we decided to start a company together. It's called CodeSpeed. And we have been building that ever since. So CodeSpeed is a dev tool aimed at ensuring that we help engineering teams measure and optimize their software performance. At the moment, it's integrated with your existing benchmarking libraries, such as Python's benchmark, and it runs on GitHub runners or even your own runners. And it can give you performance reports indirectly in your PR so that you ensure that you do not merge performance regressions. So you can see a little example here. So it's directly in your pull request. You open a pull request, your benchmark runs against your baseline, and we can directly see some performance reports. And we got a lot of trust from the communities, for the open source community, because CodeSpeed is free for open source. We got a lot of Python performance experts that are already using the tool to either optimize the performance or ensure that the code they ship is not regressing. So we're really, really thankful to have all of this support.
And so that's most of it for the sponsored part of this talk, but really excited to dive in performance and why it matters, and then in the future findings. So the biggest reason we think performance really matters is because it really impacts your user experience, whatever you're building, either if it's a library or if it's just an API that's used by a front end, or like whatever the software is. Usually performance will have a dramatic impact. And so to that extent, it's really important that you do whatever you can to make your software as fast as possible, even if some might discuss that if you're working with Python, you don't really care about performance. I think this is completely false, and there are a lot of low-hanging fruits that can be harvested to improve performance, and we're going to see this just later. And as well, it's a competitive advantage and brings you some cost savings in your cloud, because less compute means that you actually need less instances or less compute time if you're using like serverless runtimes or stuff like this. And last but not least as well, it's great to use less energy to do the same compute, because it means that you can use this energy to do something else and reduce the data center for carbon footprint, for example.
Yeah, and one thing that we learned throughout the years is that getting performance right is really, really hard. And mainly because we are not, like our computers, we are not machines. We're not able to look at the code and decide whether it's going to be fast or not. We can have intuitions, we can have an idea of what the performance of the code will be, but most often than not, even what we saw building CodeSpeed is that even the best performance experts we could find, they sometimes get things wrong, and their intuition is not exactly the same as what really happens. So that's why we had the idea of making this talk, to showcase this kind of things. So if you do not trust us on the fact that you cannot make assumptions of performance of the code, we will put you to the test. So this is the part where the talk gets interactive. So it's time to wake up, take your phones out, scan the QR code, and you will join a website where basically you'll be able to answer some questions. It will be during the whole talk, so don't stay focused on your phone as for like the remainder of the talk. But Yeah.
And yeah, by the end, there will be a leaderboard, so we'll see who is the closest to a machine to analyze the performance of the code. Okay, I think we can start. Anyway, we have a warm-up question, so we can start with it. And I'll just make sure that we... Okay. So the first question is about those snippets of code. So one sleeping for 1 second and another one sleeping for 1,000 seconds. So for all the question, it's gonna happen like this. So first we're gonna show you a snippet of code, and then there will be the question, and actually you will have to answer on your phone, and you will have the code visual available on your phone as well if you need to still have a look. So I'll start it right now. And yeah, the fastest wins more points. So you have to answer basically which one of those functions is the fastest. And so yeah, as mentioned, it's a warm-up question, so it might not be the most interesting one.
Yeah, but make sure to make no mistake. All right. So, wow. Did not expect that. Wow. It's really, really interesting. So we have a kind of a dead heat, like it's really close by. So what's the verdict?
So when we measure, we see that actually there is no bar for one of the functions. We don't even see it on the screen. But basically there is the async IO one at the top and the time.sleep one at the bottom. And so this was a warm-up question, as I said, because mostly it's just that we're lacking a no-wait statement and to have an async function. So essentially this function is not doing anything. And actually when you run it, it's just throwing you a warning like you have an unweighted promise. So
yeah, and
does it make sense?
We might have been a bit tricky by removing the wait keyword, but you'll see that things are going to get a bit weird. So we'll see.
So for the next one?
We'll start with our first case study. So we'll take a really simple algorithm. The idea of the algorithm is that we take a list of ints and we return the number of even numbers in that list. Pretty simple. We have 3 implementations. The first one is a for loop that iterates over each element, and every time it encounters an element that is even, we increment a counter. The second one is using the sum operator with a list generator. And the last one is using the len operator to calculate the length of a list, and the list is created with a list comprehension. So for this benchmark, the input size we ran the benchmark with is a list of size of 10,000 elements with random integers. So let's get right away to it. In your sense, which function is the fastest for this input?
Okay.
Is it going to be a dead heat again? Wow.
Okay, interesting.
Interesting. So the correct one was not the count sum, it was the count len.
And so by our benchmarks, it's pretty close, at least between the sum and the for. The one being the fastest is len. And the reason why, first we can have a look to the sum one. The biggest reason is that there is a context switching between the generator that's inside this sum function, which is a built-in function, so it should be super optimized because basically it's not implemented in Python directly. But there is a context switch between this generator, taking the next element of the generator, and then going back to the sum function to actually do the addition. And so this is why this one is not as fast as the others. For the for loop, essentially, is doing really simple things, but there is a huge overhead introduced by the control flow of like trying to switch and adding one to the even variable if the actual item from the array is even. So that's why this one is not the fastest, and the fastest is actually just the one with the list. We can continue this example with another question, though. So on this exact same algorithm, which of those functions is using the least memory?
Yeah, the idea being that for now we've been measuring how long it took to run some code, but it's not the single thing that we measure for in performance. We often talk about memory consumption. And the idea is that out of those three, what is the function that uses the least memory so that we can compare with the one that is actually running faster? Is it the same? Is it not the same?
And by memory, we meant peak memory. I hope it didn't introduce too much issues. Okay, so this time it's not the len one, and you've been, like, the majority is right, so this is great. So if we talk about like the results, so we'll talk about how we measured that just later. We can see that actually between 4 and some, it's really close. So there is nothing really, there is no significant difference, and mostly those don't really use a lot of variables or a lot of memory allocations, while the one with len, so basically creating a list and then finding the length of this list, is using much more memory because it will allocate an array that is of almost the same size as the input array, depending on the number of even integer. But mostly it will allocate an array, so it's mostly a trade-off. Even if it's faster, it uses much more memory. So here we're talking about like 4 megabytes against like a few hundred bytes. So to measure memory consumption on this one, we use the trace malloc built-in module, and mostly to get the peak memory in a simple way. So this is not a memory profiler or something really advanced, but this is something you can get out and use really simply on some of your functions or some places you suspect that might use a lot of memory. Here as well, something interesting to note is that the first thing we do is to force garbage collection. So we start with a clean state, kind of, and to avoid having some side effects about memories or objects that are reused later on.
Yeah, and so one of the first interesting learning that we can have is that execution speed performance is not like without a cost. And for example, in this specific example, the fastest algorithm was the one that was using the most memory. So it's always a trade-off. Well, not always, but it's sometimes a trade-off between like execution speed and memory consumption. So measuring the two, and given your use cases, choosing like either high memory consumption or slower execution time can be the right way to go. But you can see that it's not always perfect. We don't live in a perfect world. The next case study that we are going to look at is a string concatenation algorithm. The first implementation, so the idea is that we have as an input an array of strings, a list of strings, and we want to basically just concatenate those strings into a bigger string. The first one is initializing a string, and for each element in the array, concatenating the string inside the result string. And the join method is using the join method to concatenate the strings. The input which shows for that is a list of 5,000 random strings with a size from 1 to 16 characters. Oh, and yeah, as it said on the when you answer, the fastest you answer and correctly, the more points you get. So if you want to be on the top of the leaderboard, you also have to be quite fast to get the right answer.
Okay, time's up. Okay, good job. So if we have a look to the benchmarks, you were definitely right. So here we display the time, so the lower is better. And we can see that pretty much concat join is way faster than the actual addition, the actual use of the addition operator. The reason being, since strings are immutables, every time we do plus equal, we actually create a new string object, which means that actually we're allocating more memory, allocating a new object every time, instead of just reusing something we already had. And when we are using the join, actually it can pre-allocate a string of the proper size, because just having the strings array, you can know the length that will have the final string, so it can allocate it and then copy the string only once instead of having to repeat, to copy repeatedly the string multiple times.
Yeah, so it's a pretty good example of like how the standard library really optimized a function to make sure that the memory allocation is on point. And yeah, those are the two learnings. So because of strings immutability, if we create too many strings, will lead to useless copies. And as I said, like built-in functions, oftentimes they are rightly crafted to make sure that you get the most out of them. So most often than not, using them will be the faster solution in comparison to creating your own small algorithms, especially for like small small utilities like sorting, concatenating, and things like that.
So for the next one, we are tackling basically here multiplying by 2 an array of integers. And here we have 2 implementations, one that is probably the most Pythonic, which is the first one using a list comprehension, and the second one using list and map and also a lambda. So basically it's doing pretty much the same thing. The second one is more functionally written. And if you're like working with JavaScript, probably you're more used to write something like this, while for Python, usually it's mostly the list comprehension. So we'll bench this with an input of size 1 million and random integers. So yeah, just give us your best guess. And for the next ones, we're probably gonna reduce the time to answer, so it's a bit more smooth, probably to like 15 seconds, which will be easier, and we'll have more time to discuss the outcomes.
Yeah, and most of you got it correct. The list comprehension is faster than the list map. So, yeah, we can see that it's quite a bit faster than the other one. To dive into that, we'll start to go a bit deeper, and we'll start to disassemble the Python code into Python bytecode, which are low-level instructions that are directly passed to the interpreter. So any Python code, we can disassemble that and translate that into Python bytecode, which is the code that the interpreter uses. And by looking at that, we'll more closely understand what is going on and compare the two functions.
And so here, here we can see, so basically the disassembly of the list comprehension on the left and the list map on the right. So the first thing we can see is that the bytecode of the list map is actually way smaller than the one from the list comprehension, but that doesn't mean it's faster, because we just saw the result. And actually, list map is using quite a lot of built-in functions. So they are called, but we won't see their bytecode here because it's implemented in C, and those instructions are purely Python bytecode, so executed by the virtual machine, as Adrien mentioned. But the biggest contributor to the slow performance and low performance of the list map implementation mostly is due to the fact that we need to context switch once again between our map function and our actual lambda function. So every time we need to push a new frame and to actually change of context, get the result, and do this basically for the length of the list, which makes it pretty slow. Even if it looks exactly the same, it's slower because it's as well not as optimized by the Python interpreter. And on the left, we can see that even if we have a lot of instructions, it's still pretty simple, so we won't dive into all of this, but it's not calling any function, not context switching, and it's mostly an execution that is more straightforward. So next, we're gonna stay on the same. So yeah, if we take back the takeaways, mostly it's avoiding switching context. So if you can avoid using a lambda or an additional function, it will help you save. Still, it will be a trade-off in maintainability, because if you don't write any function, it will be a nightmare. But for really small piece of code that is running really often, if you can avoid putting it in a function, it will be more handy. And yeah. And so for the next one, we're gonna a bit stay in this context and talk about two implementation of the factorial function.
Yeah, so the first one is your most basic recursive function. It's the basic recursive factorial implementation, where every time we call this same function with n minus 1 instead of n. And then we created a function that we call stack factorial, which is recreating what happens with the call stack of the recursive function. So we create a stack of all the elements, and then we start from the end of that stack, and we use one element after the other, and we multiply that into the result. So conceptually, both are doing kind of the same algorithm, but in different ways. And we'll see, we'll ask you how they perform. So for the next one, as Arthur said, what we'll do is maybe close the poll at when it's 10 seconds left, so that we can get a bit faster, because I think 25 seconds is a bit long. So yeah, for this one, at 10 seconds, we'll close the poll, so make sure you input your answers before 10 seconds. Nice.
Okay, and you got it right. Okay, so we see it here, but it's not there yet. Okay, but yeah, you got it right mostly, so it's really cool. And yeah, the stack implementation is actually faster. So the reason is quite close to what we saw just before. So here are the results. So again, lower is better, is the average execution time here. And so we can have pretty much a look to the bytecode in the same way we did just before. And actually it's pretty much the same thing happening. So in one of the function, even if the code is really small, we are actually context switching, while in the other one, the flow is pretty way more linear in terms of execution. We have jumps and everything, but we don't have to push a new context to push a new frame to go into a new function. And so this, so the takeaways are pretty much the same. So recursive functions are easier to implement and easier to as well understand and read. But though there is an overhead, and as well, recursive functions have a limit. So often you will end up using a pattern like this if you want to have a really deep recursion and avoid having the recursion error that the interpreter will throw you, because actually at some point you cannot grow the stack anymore, or it's the way the interpreter is implemented, and even in lower level languages you will encounter the same problem. But the way to, like the way we showed to use a stack, will allow you to bypass those limits because you define your own stack and you can do pretty much everything you want because you can allocate as much memory as you want.
All right, and now we're going to move on to another world, which is rewriting in Rust. I was here last year, and there was so many talks talking about how someone like changes the part of their library, part of their Python app to code in Rust. So it's an ongoing trend that's really interesting because a lot of people use Rust to speed up their Python code. So we had the idea of like looking at how it actually happens. So with the main things we're going to look at is calling Rust from Python code. So the use case would be that you have a Python function and you want it to be faster, so you rewrite it in Rust. The first example that we have would be basically the example from the docs of the Rust import library, which is one of the easiest way to start writing Rust and calling Rust from your Python function. It uses Pyo3 under the hood. So the first example would be to have a square function that takes an integer and squares it. So we have the implementation in Rust, the implementation in Python. We'll test it with an input of 10,000 and we'll see how it goes. Same thing, we'll cut the countdown at around 10. So make sure to get your answers before that. Suspense. Yeah. And yeah, most of you got it right. This is an instance where Python actually is faster than Rust. So right off the bat, we can remove the Rust is always faster sentence from our heads. It's not always the case. It depends on the use case. This is the measurement. And yeah, the main thing here is that we like going from Python code to Rust code. Basically, it's not free because we do have to convert data to data that Rust can use. So here we are transforming a Python int to a Rust i32. So this is not free. This has a cost, and for small, really small functions that do not do a lot of computation, this overhead can be slower than the actual gain from executing Rust code.
And actually, it's not even the case only for Rust. It could have been exactly the same with C or C++ if you do some native modules. For really small computation, it might seem worth it, but not really, as we just saw. And so we can continue, and here with a more complicated example. So still using Rust import. And so here it's with a Fibonacci implementation, iterative one. And so with a fairly large number that would not really work well with a recursive function or recursive implementation, but here we'll just do Rust versus Python with pretty much the same implementation. And so again, we'll cut the results, like the answers at 10 seconds before the end of the countdown. Suspense. So we already have the result, but you got it right mostly. So it will appear just pretty soon. So yeah, in this instance, Rust is actually faster. So yeah, there is an actual reality between everything that we see and that we actually use every day. And so here in our measurement, yeah, it's a lot faster. Unfortunately, we don't see the graduation, but it's almost 10 times faster, which is really interesting for such a function where we actually have really low data to transfer and some really simple data as well to use. So when actually we are running the Rust code, we are just executing directly like CPU instructions without having the cost of the interpreter. While when we are running the Python code, we're running pretty much the same instructions, but it's not physical CPU instruction. It's Python virtual machine instructions, as we saw before, which means that behind each instruction, there are a lot of actual CPU instructions. So down the line, it's slower, and yeah, this is mostly it. And this is the case because we don't have the just-in-time compiler usable and used here in this example. But down the line, it should be possible as well to have on-par performance.
And another example in Rust. So here we're going to do binary search. As an input, we take a sorted list of integers. And the idea is to search a target, so the needle in the haystack, using the binary search. It's exactly the same implementation in Rust and in Python. We used a list of size 10,000 with a random sorted integers. And yeah, let's see what you think about it. I can stop it. Doesn't work. Oh, really interesting. Yes, so in that case, most of you thought that Rust was faster, but it's not. And you can see that it's not by a huge margin. It's like more than, on this example, I think it's like 3,000 times faster. So like it's really huge. And it gets even bigger as the list grows. So why? The main idea is that, as you saw, the input of the function was the list of integers. But the Python function was a list of integers. And the input of the Rust function was a vec of U64. So the idea is that when we are instantiating the Rust function, to call this function, we need to transform our Python list of integers to a Rust vec of U64. So we are transforming the whole list, like all the elements of the list, to a vec U64. So basically, we are paying a cost of conversion, which is roughly the size of the, like in O of the size of the list, whereas the algorithm that's underlying, the binary search, is in log of the size of the list. So as the input grows, the Rust implementation becomes even worse because we are copying a lot of data, converting a lot of data, but not actually using a lot of it. But fret not, there is a way to overcome these kind of problems. So the idea would be that instead of, so on the left, you have the previous code that used as an input the vec U64, and on the right you have another code. Basically, we simplified it and we only showed the parts that changed. And there, as an input, instead of getting a vec U64, we are directly using the Pyo3 types, which represent the data as it's mostly as it is in Python, so that there is no conversion of any kind. And the only time we are actually doing the conversion is when we are retrieving a value. So instead of converting the whole list, now we are converting only around log n elements. So I gave you the answer, so we won't ask you a question this time. And you can see that, well, it's even harder to see, but the Rust function is on the bottom. The newest Rust function is at the bottom, and it gets magnitudes faster than even the Python one. So for this kind of use cases, the learning is that when you are rewriting parts of your code in Rust, be really careful about what data you transfer from and to Rust, or as I said, like any type of other languages, low-level languages. And yeah, be careful of that. Be careful of that, especially like if your algorithm is using less data than the actual data that is transferred. For the Rust example, the assembler, the native code of Rust will most likely be faster than the Python interpreter code. Yeah, I already said that about the data type. So yeah, that was it for Rust.
Yeah, and we reached the end of the quiz, so now it's the time for the leaderboard. I don't know how it's gonna go out. Okay.
Wow. Okay. So who's Derek?
Nice.
Thanks. Quiz? Yeah.
Nice.
All right.
Good job.
So if anyone in the room is trying to hire a performance expert, I think you have that man to go to talk to. And even the other like people below, like they're really interesting. So yeah, really like huge congratulations.
I don't think we have the rest of the leaderboard. Probably you have it on your phone. I mean, it should be possible. But yeah, really cool. Congrats. And so for the recap, mostly as we said in the beginning, it's really hard to guess the performance always, except if you're that guy. But otherwise, it's really interesting and important to actually measure and either measure memory usage or as well just the number of instructions that are executed, or purely and simply the wall time that it takes to run the code, because it will as well depend on the architecture on which you're measuring, which is something we didn't treat here in this talk, but depending as well on the architecture, the CPU brand you're using, it might, or on CPU type, it might change. And as well, depending on the data, some algorithms that might be faster than the others, so trying to think about what kind of data will be used by the algorithm you want to optimize is really important.
Yeah, and as it's written 3 times in this slide, the only way to be sure about performance is to measure. So always, always, always measure. And yeah, that's it for the talk. So we do have a booth down in Hall A. In Hall A, so be sure to come by and say hello. We just released a new performance lab. There is a QR code there. That's actually the performance lab. That's the software we use to run all the measures that we showed you during this talk. Were made with this performance lab. So it's pretty interesting, pretty cool stuff. We just released it today, just for the PyCon US. So all of you that are scanning this and accessing it would be one of the first users. So we're really open to the feedback. It's be kind with us. It's we just released it today as a public beta, but really eager to see what you think of it. So be sure to come by the booth and talk to us about it. And yeah, really thank you guys for coming. And yeah, we can open. Well, thank you guys. Sorry.
Yeah, thank you.
We have 2 minutes for questions. Raise your hand, I'll come to you. In the back.
Hello, I was just wondering if these learnings also apply to other Python implementations besides the CPython one?
We mostly tested, and we exclusively tested with CPython. So as you mentioned, it would be really interesting to test with as well, maybe PyPy or something like this, because as we discussed, the JIT could have a significant impact on some results. So yeah, definitely, especially for the Rust cases, I think it could be pretty interesting. So yeah, we'll try to add this because it would be really interesting.
Okay, sounds good. Thank you.
Anybody else?
Thanks for the talk. Very interesting to see. I know one of the things that you stressed is always measure and don't just trust human intuition. But on the intuition side of things, I'm just curious, like generator versus comprehension. Like basically, unless you have a memory constraint, usually will the generator always be slower because of that kind of having to like switch context, because that seemed to come up repeatedly?
I'm not sure to have understood the end of the question.
Oh, sorry. What I was saying was, as a general rule, will generators usually be slower unless you have like, if you're not like bounded by the memory because of that context switching compared to a comprehension?
I'm not sure. I would guess that depending on the amount of data you have and the operation you're doing, because what we showed was really some simple examples, multiplying a list by 2, for example. So in this case, specifically, the overhead of switching from one context to the other was really massive against the overall cost of the function. But otherwise, in some other cases, it will probably be more useful to actually use the generator and try to consume it instead of building a whole list like we did before.
But like, if your end goal is to create a list, of course, like building a list comprehension will be faster than like going through a generator and then converting that to a list. So, of course, as you said to the beginning of the question, like we don't have to discard intuition, otherwise, like we would just like never get anything done. So it's good to have intuition, but it's better to check your intuition with a measurement. So,
Thank you.
Okay, let's give these folks one final round of applause.